Hello, everyone. I hope you had a good break. So we now have the last session of today's schedule. Just a reminder that we start again 8:45 GMT, and that's the last session. So we have another plenary and a set of short talks. And we will also have an extended discussion after that. So if you're interested in joining that, please do stay around. So for the remainder of today's session, we're joined by ALLISON OKAMURA. So thank you very much for joining us. It's really fantastic to have you here. And then we will invite back some of our panel speakers for a final discussion. So please do stay around, panel speakers, if you have the time. So it is my great pleasure to introduce ALLISON OKAMURA to give her talk on understanding and designing for human haptic intelligence. So thank you very much, ALLISON, for joining us. And I will hand over to you.
Thanks for having me. While many of you are ending your day, I am starting mine. So hopefully I'll be able to bring some air to what I'm sure has been a long Zoom day. Josie, can you confirm that you can see my slides okay?
Yes, that's perfect. We can see and hear you very well. Thank you. I'll leave it to you.
Wonderful. Well, I'm very excited to be here. I haven't normally thought of my work so much in the context of embodied intelligence. So the work, as many of you might know, that I do spans human haptics, perception, and interaction, as well as soft robotics and rehabilitation and other medical applications like surgery. And this talk, I debated a bit on what I should discuss here, but I thought I would, in order to maybe be a little bit different and try to connect to the human experience, that I would talk about the way that we think about providing embodied haptic intelligence for humans interacting with virtual environments or remote people or remote teleoperated robots. And I noticed my title was quite similar to Catherine Kuchenbecker's, so I was somewhat relieved to be able to review her talk and see that what she discussed, I believe it was yesterday, was focused more on robots using haptic intelligence, still for human-robot interaction. Here, I'm not going to focus on the robotics side so much as what we can do to provide useful feedback to humans. So I wanted to, first let me, before I get started, let me just thank the students and postdocs and former students and postdocs who have been the primary contributors to the work that I will discuss today. So I want to start by thinking about what does it mean to have a remote or virtual embodiment for humans. So I'm imagining scenarios where you have a remote presence or you're using a virtual tool and where it's augmenting a human with technology, and how should a person feel in order to have this embodiment? So a few ideas, and these actually also came up simultaneously this week. We have the IEEE Haptic Symposium conference going on, and there was a cross-cutting challenges workshop yesterday that was also discussing haptic embodiment. So I was happy to see that any of you can access those talks as well. They will be available for free. They were also recorded. So in any case, in that session, there was a discussion about what means embodiment in this case. It involves ownership. So if there's a remote or virtual object that represents you, you feel ownership of it. In particular for haptics, we're interested in intuitive force motion relationships, and not necessarily large scale forces that push back on your arms and hands, like when you're lifting a heavy object, but also minute ones, like for texture, things that just stimulate the skin. So all sorts of scales of force motion relationships. And then there is the idea of feeling agency and authorship, that you have expected consequences of your actions, and that you receive appropriate feedback for them. And I think this is somewhat related. I didn't have a chance to watch it yet, but I saw that Daniel Wolfert also gave a talk to this group, and this idea of expecting consequences of your actions and how maybe a different consequence affects learning or adaptation is also a key part of this. So another few things to say about embodiment for humans. It can be conscious or subconscious. And I also want to note that it can be somewhat hard to measure. And while the ways in which we typically measure it in our lab are going to be about performance and perception and ability to kind of have these skills connected to what happens in a virtual or remote environment, there is another way to do it. And the classic example that many of you may be familiar with is the rubber hand illusion. So I'm going to play a video in a second for anyone that hasn't seen it. But the idea is that you have a person who has their real arm there, and then we have a rubber version of the hand, an artificial hand. And what the user, the subject, sees is the artificial hand, but there's a series of sort of tactile, haptic interactions that occur that causes the subject to have an embodiment of the rubber hand. And then you will see at the end how they test this. So in this video, the real hand's behind a curtain, and the rubber hand is what the subject sees. And then there's some tapping and stroking and moving that occurs both visually in both the rubber hand and the real hand. And then to test embodiment, someone will harm the rubber hand, and the person reacts strongly because they've embodied that rubber hand and they feel like it's part of their own. So that is definitely one way to test embodiment, but it is a little challenging to sort of quantify the level of embodiment. So my caveat in the work that we do, and much of the work in haptics, is we don't directly measure embodiment in this kind of way. Instead, we look at performance and we try to understand, do people perform similarly with the haptic feedback that we provide as they would in the real world when they're directly interacting with mechanical systems. The other thing I mentioned, and I thought this was a nice description from one of the speakers yesterday at Haptic Symposium, was that humans are very good at interpolation, but not so good at extrapolation. And so I think that is a nice lesson for haptic embodiment for humans in terms of providing the necessary feedback and kind of the boundaries of what people should feel, because folks may not be able to extrapolate beyond the maybe multisensory feedback that you give them. So to begin thinking about this, what are our goals when we design haptic devices? So primarily, I'm interested in how we create physical connections between people or objects that are either physically remote or remote in scale or time. So one interest, especially during the pandemic, was being, how do you create human-human physical connections? So here's an example of two people interacting, and haptic feedback is allowing sort of natural interactions, more of a social nature. Sometimes the interactions might be more informational, such as when I have a map telling me which direction to go. It would be great if I didn't have to call my visual attention to that map and instead get directional information through a wearable device. My Apple smartwatch actually does do this, but the haptic feedback is usually not detailed enough or understandable enough to give me information about which direction to go. So usually what it does is it provides an alert which tells me, oh, pay attention, there's a turn coming up, and then I change my attention to visually look at the map. And to me, that's not embodiment. It's not something that it's really become part of my sensory motor control loop. It's just an alert, and that's primarily what vibrations have been used for. So we would like to provide more detailed information that becomes sort of a natural form of feedback that people can follow without relying on other sensory cues. And I will say, although I'm a haptics researcher, I'm not a believer that everything has to be haptics, but there are definitely cases like driving where we prefer for people to keep their visual attention on the road and understand also how other forms of feedback might remove attention from that. The last type of interaction I want to mention is human-robot interaction. I think Catherine covered this very well, especially as robots around us become more ubiquitous, more autonomous. Are there going to be some nice, convenient ways of having interactions, whether they be directly physical or remote, in order to have natural communications, and again, not necessarily pull, say, visual attention away from a primary task. Now, some of this, of course, is already there are these scenarios where people lose haptic feedback when they're interacting with a remote environment, whether it be virtual or teleoperating a remote robot. So these are all cases that are somewhat specialized, but you imagine, of course, a prosthetic arm, which is a very natural place to talk about embodiment. But also robots for demining, robots in space so that astronauts can avoid doing a spacewalk, and teleoperated surgery where instruments can go deep into the body and be able to manipulate effectively shrinking the surgeon down such that you don't have to cut such large holes in the patient's body. And these are all very specialized situations, either a medical situation or a professional situation. But of course, the lower right is virtual environments as we think more about the metaverse and what we want out of it. In what ways should we be embodied in these immersive virtual environments, and what combination of haptic and visual information, as well as sound, taste, smell, whatever senses may want to be included. How do we do that in a way that is appropriate? So historically, in the field of haptics, in addition to the vibration feedback that I mentioned, there has been great interest in kinesthetic or force feedback haptic devices. And I just want to introduce that here, but the vast majority of this talk is not going to be about kinesthetic devices. Instead, I'm going to be motivating other types of devices. But to put this in context, for kinesthetic devices, we are thinking about haptic feedback devices that are much like traditional robots, except that they are back drivable. So you grab an end effector, you move it around in space. The motors, depending on your position, will apply a certain force or impedance, and you will feel virtual objects like the sphere that's outlined here. And even today, for folks that have not felt this kind of virtual environment, it's amazingly compelling. And you really feel a sense of embodiment in terms of the virtual tool that is being represented in that virtual environment really feels like a tool that you're holding in your hand. It doesn't necessarily feel like you're directly touching things with your fingers, and we'll get to that in a bit, but it does feel like you are poking at a world with a tool. It just is not one that you can see aligned with your physical hand. If you combine this with graphics and sound sometimes, then the illusion is really complete. So these are fantastic, but as we are interested in developing more, I would say, ubiquitous haptic devices, ones that we can use in our daily lives, ones that can actually be consumer products, as opposed to a few $1,000s or tens of $1,000s in the case of this kind of phantom premium haptic device. We really need to think about other directions. And so we have really focused in my lab recently on cutaneous or skin-based feedback. And to motivate this, I'm showing here a set of really old videos, only the left one is playing right now, of from Roland Johansson's lab in Umeå, Sweden. And in this early work, he was demonstrating the importance of the skin-based feedback in performing, I'd say, minute dexterous tasks. So while pushing on a virtual sphere and really feeling large forces and stiffness properties might be important in some virtual scenarios, there are simple things like grabbing and lighting a match where you don't expect the forces to be very large. And it's really local contact conditions that matter. So the video that's playing now, a woman grabs a match, lights it, very simple, easy to do. And then her fingers are anesthetized, and it's really only knocking out the mechanoreceptors embedded in the skin that in a minute I'll describe what they do, but they are providing more high frequency local information. It's not affecting her vision. It's not affecting her ability to move. It's not affecting her ability to sense large scale forces. From this anesthetization, she's only losing information about local contact and skin sensing. And now you can see from this video, I hope, that she's having a really difficult time. She can barely pick up a match in order to get it solidly within the grasp. And then finally, she manages to get a really good kind of form closure on it, grasping it really tightly. And then eventually she is able to light the match. But you can see how much more work it is. And this is something that is obviously important for autonomous robots, but it's also important for thinking about how we provide feedback to humans. So what is involved in cutaneous sensing? Well, the mechanoreceptors in the skin, there are many different types, but I'm just going to highlight some key properties here. They have different densities in the skin depending where you look, and this will be very important as we think about haptic feedback, not just to the fingers, but also to other parts of the body. They have different spatial distributions. The different individual mechanoreceptors have different responses to different frequencies. So the pacinian corpuscles, for example, get very excited when we are subjected to high frequency vibrations. And this is primarily what is sensed when we have, for example, local slip, as well as vibrations from technology. And the type of skin also affects very much which mechanoreceptors are involved. So the glabrous skin of the hand and the bottoms of the feet have a higher density and more different types of mechanoreceptors, whereas other places where we might want to mount haptic devices, especially as we think about eventual consumer products like the arm or the back or the legs, are going to have hairy skin and have reduced haptic sensitivity due to reduced numbers and types of these mechanoreceptors. So as we then go to saying, how do we design haptic devices? Let me start with an example which I think doesn't really have anything to do with human embodied intelligence, because it is a very literal way of providing haptic feedback. And that is combining both kinesthetic and this tactile or cutaneous feedback. So what it is using active surfaces, whether they use soft robotic techniques and particle jamming, like the video from my lab that I'm showing on the right, or they're recreating the shapes of surfaces as shown on the examples on the left. These systems are just literally trying to recreate the world. So the person doesn't really have to embody anything about this. They are just using their own hands to interact with these objects, which aren't even really virtual objects. They're physical objects that could maybe be augmented with graphics and such, or augmented reality scenarios. But the idea is that there's not really a question of embodiment here, because you're just trying to recreate the world for the human. So I sort of wanted to use this as a counterexample of, while kind of fun and interesting, I think is really not what we want to do in the long term. It's very difficult. It's a very literal, complex way of thinking about providing haptic feedback. And if we want to engage haptic illusions and make devices that are simple and small and wearable, we need to understand better how do we create haptic illusions to create this feeling of embodiment by tricking the user, essentially, rather than recreating the physical world. So this is the counterexample. So I'm going to sort of start simple and get a little more complex as we think about ways that we can generate haptic illusions that affect what a human feels. So I mentioned earlier that vibrations are typically used as an alert, just an event signal that draws someone's attention. But it turns out you can do more with vibrations. And this has been done by our group as well as several others, where you use asymmetric vibrations on the lower left there. Instead of having pure sinusoid type waves, we kind of go hard in one direction and then recover more slowly. And if you get the wave pattern right, what the person will feel through, for example, a voice coil motor or a set of voice coil motors that can be apply the tugs in different directions, is the user will feel a tug in the direction of the fastest acceleration. So they'll feel sort of a tug, 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 and that gives you directional information from vibrations. Another way, of course, to provide directional information from vibrations is to provide vibration feedback at different locations on the skin, and that also works. But if you're trying to minimize the number of actuators and kind of bring them together into nearby locations, this is an effective technique. There's another thing I want to mention about these asymmetric vibrations, which is really interesting, and that is that when you get these asymmetric vibrations, some people, but not all, it depends on the circumstance. We found it doesn't work as well with older people who have diminished sensation of vibration. But for some people, they not only feel the tugging direction, they actually feel compelled to move. And this is related to something known as the hanger illusion. It's a bizarre thing. You can look it up on YouTube. People put a wire hanger on their head and twist it a little bit, and something to do with the skin stretch and the placement causes people to want to turn their head. So there's this similar feeling of the tugging. It's not just telling you the direction in which to move, but also giving you the feeling that you want to move, which I think is very intriguing. And there are several haptics groups now who are trying to really fully understand, you're just going beyond a sensory illusion, what creates the sensory motor illusion and the desire to move with this kind of feedback. Because ultimately that's sort of what we're looking for in embodiment, right? Is that the person wants to do a certain thing based on the feedback that they get. So going much more complicated than vibrations now, we have this idea of effectively putting small 3 degree of freedom or higher robots on the fingertips of the user. And this was inspired in large part from early work from Domenico Pratechiso's lab, where he thought about the idea, he and his students thought about the idea of sensory subtraction, that, okay, you have this fancy robot desktop haptic device that provides this kinesthetic feedback and detailed force displacement relationships. But what makes these devices expensive in large part is having these grounded motors that need to have very high torque constant and be able to do that for sustained at long periods of time without overheating. So what he felt is that what Domenico Pratechiso felt was that if you provide just local skin feedback and you subtract away the kinesthetic world grounded forces, or in the case of an exoskeleton, even body grounded forces, and we really focus not on displaying forces over a joint, but just deforming the skin. It's still body grounded in a sense, but we're just deforming the skin, that you can provide this compelling feedback. And I really wish we were together in person and we could be doing demos of this kind of thing. But hopefully you can get an idea, especially by looking at the video on the right, how the feedback would correspond to manipulation in the virtual environment. And we found that people very easily understand this feedback, even if they get no kinesthetic feedback. Just by getting cutaneous skin feedback, they can perform very naturally, and they can also discriminate mechanical properties. So for example, if we ask you to change the mass, people can notice it of the virtual objects, or stiffness or friction. But even more important than those sorts of psychophysical tests where we ask people what is, to find the just noticeable difference of specific mechanical parameters, we wanted to know if this type of feedback feels natural. Do we actually have the illusion, this sort of embodiment of your fingers are in the virtual environment and manipulating the virtual objects? And we did that by not just asking people how much difference in mass do you feel, but by secretly changing different properties, whether it be mass or stiffness or friction, and then asking people, what's the difference between these two blocks? And we would get kind of different answers depending on if the person was an engineer and thought very technically, or if the person was not and just sort of spoke in more natural language. But we mapped how people responded to what we thought they perceived was changing versus what had actually changed. And people did a pretty good job with this. So what this plot on the right here is trying to show is that the thick lines are where many, many subjects responded, and the thinner ones were where very few subjects responded. So you can see that most subjects responded when we changed mass. They thought that mass had changed. And this is without any other prompting, just said, what changed between these two objects? They might say weight, they might say mass, they might say heaviness. All of those things were mapped to mass. Similarly with friction. So the interesting thing about stiffness is that that was a little more confusing. So a lot of people thought when we changed stiffness that we changed mass. Some did think we changed stiffness. Some also thought that we changed something like friction. The interesting thing is that despite these errors in the human perception, it turns out that when we did the same experiment with real world objects, people made the same kinds of mistakes. And so for better or for worse, a kind of haptic illusion that functions correctly is going to do the same thing in the virtual environment as it does in the real world. And that turned out to be the case here. So I know that a lot of folks in this audience design devices as well, right? Using soft robotic techniques and such as ways to think about embodiment. And so as a kind of maybe different take on the relevance of this work, I thought I'd show some other types of devices that we've been developing in order to achieve these kinds of fingertip skin deformation. So we've been wanting to figure out how do we make the devices smaller, simpler, cheaper. So one way has been to go towards origami construction, and that has definitely improved in the size and the weight and the assembly process. Although the example shown here still has motors, which are tiny but very expensive still. I'll note that this origami device, in comparison to the one I showed in the previous slides, this actually has 4 degrees of freedom. So not only does it do X, Y, Z forces, but it also does twists. So if something twists within your fingertips, like this pen twisting here, that is something you can now also feel with this device. So it's kind of a smaller form factor and even adds a degree of freedom. We may even want to go to a full 6 degrees of freedom, but it depends on which ones you think are most important for the task that you want to display in the virtual environment. I'll note, although it's not ready for prime time yet, that we're looking at various pneumatic actuators to replace the motors as well. Very recent work, in fact, this will be presented at RoboSoft in a couple of weeks, is now taking this origami technique and I say sort of because it's pneumatics, which means there's a compressor that's off the screen that we're not showing, but sort of shrinking it down into an even smaller device. So my postdoc, Zenish Sakipov, developed this fully 3D printed soft fingertip haptic device that also has the same degrees of freedom. And it's an interesting combination, kind of like some things that Kyujin Cho had done in the past, where you're combining soft robotics with origami techniques. Some people include origami in soft robotics, but soft materials included with origami techniques, and using the sort of interesting water bomb origami structure in order to achieve this small form factor. And the cool thing is that it is 3D printed, so we can print sets of multiple ones at once. This one was 3D printed on a Formlabs. So I do think making these small wearable haptic devices, notwithstanding the open challenges of the pneumatics aspect, we can take great advantage of 3D printing, and even new techniques such as embedded 3D printing are all things that we're looking at. So those were a bunch of fingertip skin deformation devices for, say, manipulating objects in virtual environments. It is interesting to think about using the skin deformation also for navigation and not just feedback. So this is sort of akin to the previous example I gave of the asymmetric vibrations, where you get tugged in a particular direction. And I thought this was sort of interesting in terms of embodiment, because of the way that people, I guess, transform haptic information and how they interpret it. So here's an interesting plot that shows how people interpreted haptic feedback at the fingertip in terms of pulling them in particular directions for this, in this navigation scenario. So we would give them haptic feedback, plus or minus 180 degrees, and then we would ask them, which direction is it tugging you? And it's not a straight line. People will tend to go towards the cardinal directions. You can kind of see that from where the flat areas are, for a certain range of input haptic tugging angles. They will tend to think, I want to go forward, or I want to go right or left. And this really is an effect of how people interpret the haptic feedback, because if we gave them auditory feedback and then had them point in directions, it was a straight line. And so we would learn these kinds of human responses to haptic cues, and each individual has a curve that's a little bit different. It probably works okay to have an average, but it is kind of interesting to have a personal optimized haptic response curve. And we found that if we wanted people to walk around from a starting point to a target by following these haptic cues, if we followed the sort of naive leftmost method where we just tug in the direction we want people to go, they would have to kind of, do some circumventing in order to be able to get to a target. And this is when they don't know where the target is other than the finger pulling them, essentially. When we optimize it based on a learned model of an individual human's responses, then they do much better. And then we said, well, maybe we don't have to tug on them all the time. Maybe we can just tug on them when they're going in the wrong direction. So when we do that as needed, it turns out that we can still do pretty well, but not as well as when we're always giving them feedback. And we can extrapolate this to higher degrees of freedom. So when we do this with 2 fingers, now with a holdable versus a wearable device, and you provide all kinds of different combinations on the left and right fingertips of this skin tugging through these devices, you can get people to move in many degrees of freedom, which could be interesting for all sorts of applications, ranging from surgical training to, again, interacting with objects in virtual environments. I think this is a bit of an aside, but I wanted to mention it because it's one of our projects that I really love. And that is also thinking about embodiment from the aspect of how do you understand mechanical properties of the world. So if anyone is interested, we have this haptic device. There's been some supply chain issues, so not all the parts can be currently ordered, but we're working to find alternates. But the idea is at hapkit.stanford.edu, you can find the parts to and instructions and details to build a simple 1 degree of freedom haptic device. And we have put these in classrooms and had children ranging from elementary school to middle school learn about mechanical properties. And so on the education side, it's kind of cool because you use 1 device to do a lot of different types of, say, physics or math experiments. But on the other hand, there is this sense of embodiment, right? That green hand that's going up and down on the image that's pulling on the virtual spring is your hand, and you get to experience different mechanical properties that allow you to do a kind of virtual lab. But I think an even more fun thing is that a student can program their own virtual environment, right? They get to play physics god. They get to decide gravity goes this way or friction is negative, and then they can explore and see what happens. And so we think that there may be some really interesting aspects of kind of tacit and experiential learning that occurs when you're embodied in this virtual experience and being able to connect the equations that you program into something that you feel. So that's the main gist of it. We've extrapolated these to higher degrees of freedom with different parts. And again, all these designs are available at hapkit.stanford.edu. And there's some other form factors where we're also trying to teach math concepts. So let's move on though, from going to the fingertips, since we've mostly been focusing on devices that interact with the fingertips, to devices that we think could be more ubiquitous in the future if they are mounted on the arms. So as I mentioned, depending on if you're in glabrous or hairy skin, you have different densities of mechanoreceptors, and these purple dots are not meant to indicate some kind of disease, but some idea of the distribution of mechanoreceptors. So on one hand, we have a challenge in that we don't have the same tactile sensitivity on the arm as we do on the hand. On the other hand, we have this advantage that we have all this skin real estate to work with. It is hard to pack actuators into a small location on the hand or the fingertip, but here we do have a lot of space. We're concerned about comfort and weight and size, but we have space to work with that is essentially unused real estate on the skin. There's another interesting aspect of this, which for some cases I feel like we've figured out, and other cases we haven't, and that is that the human hand is ideally suited to active touch. And I think this is really key for embodiment, right? Is an agency and authorship, right? That you get to explore the environment in the way that you want. And Lederman and Klatsky famously demonstrated several decades ago that people have particular exploratory procedures they use. So if I want to understand the texture of my water bottle, I'm not going to hold my hand statically there. I'm going to move it back and forth with a particular velocity that will excite the mechanoreceptors that will most tell me about the friction properties or texture of that surface. And that active touch, the being able to do anything you want in a virtual environment and have the system respond appropriately is important to that agency and authorship that brings us to this haptic embodiment. However, other parts of the body are not really designed to do that. So we're not used to, just kinematically, it's hard for us to explore the world with our arm. And if we are, for example, sending haptic emojis, as I will discuss later, like we're being passively touched. We're not part of an interactive loop. And maybe that's okay in some circumstances, but it won't really cause embodiment typically. So we'll see some examples where we are able to use the fingers to explore and get feedback in another location, and it really does feel like active touch. But I think there's still a lot of questions to be asked and answered about passive versus active and locations on the body. Okay, so I think one thing everyone should know is that haptic feedback, of course, is better on the hands and other parts of the body. One of the ways in which we test this is through a monofilament test, where basically you poke at people with some wires and you measure their tactile sensitivity, like can they feel it or can they not? And this is something that we've done in a number of populations, but interestingly, one I'll talk about in a little bit is someone with a spinal cord injury. As we're trying to figure out where we can provide haptic feedback, we did this set of tests. So in this example, for this person with a spinal cord injury, they had a brain gate implant. So they had an electrode array implanted in their cortex, measuring neural activity. This is work from Krishna Shenoy and Jamie Henderson's lab here at Stanford, which we collaborate with. They have a neural signal decoder, which gives a command signal, and that lets their participants control a cursor on a screen or control a robot arm or type on a phone or a virtual keyboard. And what we were doing based on our measurements of where a subject had intact sensation is we were providing haptic feedback. And the case that I'll describe here, we were actually providing haptic feedback to the back of the neck, because not only did they lack movement, but they actually lacked sensation as well from about the collarbone down. And we found that we could get responses. Oops, thought we were going to have some responses there, but we could get responses in motor cortex. We can provide haptic stimulation at the same time as this invasive brain-computer interface is being allowed to continue, and it doesn't interfere with BCI performance. So to show you what this looks like, here's a video where the subject is thinking, I want to move the cursor to a target, and the brain-computer interface is neurally decoding. And you can kind of see on the lower right here is a heat map showing basically the matching of actual stimulus direction to their predicted stimulus direction. So it's not perfect, but it's pretty good. And then we also measured their shear perception accuracy based on the haptic feedback that they get. And interestingly, it almost matches the neural decoding ability, although that was not intentional. So the interesting thing here is that qualitatively, the subject thought that the haptic feedback was useful and therefore sort of improved their embodiment in terms of their ability to control the cursor. And it did actually help their performance. I would say a relatively small amount, and we think that's because the task is relatively simple, and we're looking forward to doing these kinds of experiments with more complex tasks and ones that more inherently involve mechanical interaction, like controlling a robot arm to grip a cup, for example. And I will say, if you look at the literature on this type of BCI control, there have been amazing demonstrations done, but they're typically not about embodiment. They're typically about switching, right? So a robot arm might have an autonomous subtask to reach out and grab the drink, and then another one to lift it to the mouth. So we don't really have a tight sensory motor control loop yet demonstrated in the literature for these kinds of devices. And we think with haptic feedback, we will be able to have sufficient embodiment such that we can move on from this sort of user sends a command and it switches to another aspect of the task to something that's more akin to a natural human sensory motor control loop, which is what the subject is doing when they're doing the simple center out cursor task. So that was one example of moving by the fingertips. So it was very specialized, right? Moving to the back of the neck. Let's, in the next few minutes, think about some examples of moving away from the fingertips, and in this case, using the finger to explore the environment, but providing the feedback at another location. And I realize I'm running out of time, so I'm going to try to hit these last points sort of quickly. But the main points are that participants can still identify virtual object properties. I'm going to skip a bit ahead to say that we're interested then in knowing what are the right locations, right? If we want to have this embodiment, do we map this finger to this location and this thumb to this location, or can we map in different ways or even reduce the number of actuators needed? And this is sort of hot off the presses work that we just submitted. And our results so far are that we didn't actually see a difference in performance from the mappings. And so we can't really argue currently that we improve embodiment based on these different mappings. And it might have been because the task was too simple, but there may be other reasons. But the interesting thing in terms of preferences in a more subjective survey is that people did more prefer congruent mappings, like the kind of mappings that you would expect in terms of location. And this is exciting because it's showing that people can reuse relocated haptic feedback from the fingertips to other parts of the body. And it might also indicate, some of the very interesting work that's been done in prosthetics, right? Like instead of a typical hand prosthesis, what if you have something that looks more like a tentacle, right? How do you embody these other shapes, but also the haptic feedback that you get from those shapes of devices? We've also done a lot of work, and I'm just going to breeze through these and just show a couple of videos of examples of soft wearable haptic devices where partially we're trying to explore the manufacturing and control techniques, but also we're exploring how many points of feedback and how many directions and trying to understand how those affect embodiment. So some of them use traditional soft robotic techniques like fiber reinforced actuators. Others use things like our strange soft growing vine robot, but in a more of a bracelet form factor to deliver small pouch motors at different locations on the skin. Others combine soft and hard components as shown here on the left in order to provide more degrees of freedom. And this device also highlights the challenges that when you have a wearable haptic device, you have to provide appropriate reaction forces, and understanding how to do that correctly. This is probably not the final solution, but here we use some hard components so that we can definitely provide the necessary reaction forces, but still use soft actuators for interaction with the skin. Other examples here, this is work in progress on the right, kind of riffing on our 3D printed fingertip haptic devices, now looking at 3D printed wrist haptic devices. So all of these, I'd say we don't really know about the embodiment yet because we've been working on the manufacturing techniques and not yet fully understanding and testing their effects in virtual environments. So the last thing I want to talk about, just to mention a kind of different type of embodiment, is social touch, right? Things I've been talking about have been very practical about manipulation and such, but especially during the pandemic, the social aspect that I brought up at the very beginning of touch is really important. And so this is me stroking my husband's arm, showing one prime example of a social touch gesture. And if you wanted to recreate this with a robot finger, it would go down, touch the arm, and slide. But we want to know, can we design a wearable device that can, give a sensation of interaction of this kind of social touch? And it turns out you can do so pretty simply. This is not going to be a commercial product. It's still way too big. But the interesting thing that we found is that a very discrete set of simple 1 degree of freedom voice coil actuators, and if their timing is done just right, can feel both continuous and pleasant on the skin. And I'm going to skip ahead to show what we did with this. We measured actual physical social touches between people on a capacitive array sleeve. We mapped those measured social touches onto a very simple 2x4 array of voice coil motors. And then we tested subjects to see, could they recognize the social gestures that were being made, and how did they map them in terms of valence and arousal. And people did amazingly well at this. Not perfect, but we did very similarly with our device to how humans interact with other humans. In terms of valence and arousal, you can see that you would, these different emotional cues sort of fall where you would expect. So for example, sadness has low arousal, low valence. Attention and happiness have high arousal, high valence. And just a quick example of one social touch would be for attention, you would poke someone typically. We didn't tell our subjects when we took the data what kind of social touch, what the motion should be or the forces should be. We just told them, try to get your partner to pay attention to you by using the sense of touch. And so there was definitely some variance. And so it's interesting how well this mapped. So I'm going to skip over a couple more details here, just so I can end with what I see are some of the big challenges of enabling this kind of haptic embodied intelligence. One is on the device design side. We found that perceptible forces, especially static ones, usually require large reaction forces, and then sometimes people notice the reaction forces and not the forces of interaction that we want, and that breaks the illusion, it breaks the embodiment. In perception, human touch is very sensitive, but it's also easily fooled. And so, and we don't understand really over the long term how people learn and adapt to these sensations and how that affects embodiment. And finally, interaction design. If you were to ask us, where are we going with this, in addition to things in the hardware and 3D printing and such, in terms of concepts for how we use haptics, we're really interested in augmented reality, which is a unique challenge because we want to provide haptic feedback to change the way things feel when the human is actually interacting with real physical objects. So let's say you're interacting, I'll use my water bottle again, you're interacting with this water bottle and you're squeezing it, and then we provide a haptic feedback, say in another location, because we don't want to interrupt the ability to manipulate with the hands in augmented reality, we provide feedback here. Can this feedback somehow that we give here on the wrist modulate the feedback that you feel at the fingertips? And there's this kind of idea of embodiment that might be serial. Maybe you get feedback in one location, then another, like on the fingertips and then on the wrist. Or do you in parallel feel things with the fingertips and then get haptic feedback at the same time somewhere else? And how does that affect your embodiment in this remote or virtual task? So there's the metaverse, I think, is raising a bunch of questions for how we do this correctly. And with that, I want to thank the students and postdoc whose work was featured here, all my collaborators and the sponsors. And I know it's time for the discussion, but I'm happy to take some questions and participate in the discussion as well. So thank you.
Thank you so much, Allison. That was a really wonderful presentation. It touched on so many other issues and topics that have come up in the conference, so it was really well placed, so thank you. I think just before we go into the group discussion, I think we have a couple of interesting questions which I think will nicely segue us into that. I think what you already touched on, which was very interesting at the end, is how haptics can transfer emotion or social interactions, not just the sense of touch. If you start combining haptics with other visual cues or haptics with temperature and sensor, other kind of sensations, do you think we can really transfer emotional connections or use haptics to provide a virtual connection between a virtual presence or a human, for example?
Yeah, I definitely think so. You know, our experiments have not really addressed making that emotional connection, right? It was more about recognition and sort of pattern matching on the human side. But yeah, for a true embodiment, you would want to measure someone's emotion, essentially. And other researchers have done that and had some promising results. They use things like heart rate and galvanic skin response in order to see, you know, can you actually measure physical signals? As well as have, you know, more subjective interview processes that might say something about the level of emotional engagement. But we definitely think that's possible. And probably, as you mentioned, the multimodal aspect is going to be key for having that immersion. I think the other point I want to make is the social touch example I gave. It's really like haptic emojis, right? We recorded a bunch of signals and we just played them back. You know, we and other groups are looking more at how do you do this in real time? How do you sort of teleoperate haptics? And in that case, to what extent, yeah, is there embodiment is an open question.